In this video, I want to talk about the action potentials of neurons. Here we have our neuron with her soma in red and a larger than normal axon in green, and now I've drawn a myelin sheath in yellow around the axon, and a couple of larger than normal dendrites in blue. And here's our graph with the membrane potential on the y-axis and time on the x-axis. And we've been talking about, in the absence of input, most neurons have a stable potential across the entire membrane that I've shown here, which is often around negative 60 millivolts. And without input, the resting potential will just stay right there. But excitatory or inhibitory inputs, which usually come in through the dendrites, but less often can come into the soma or the axon itself, will cause changes to the resting potential that we call graded potentials. That may be either a depolarization, also called an excitatory potential, or a hyperpolarization, also called an inhibitory potential. And these are called excitatory or inhibitory because they involve movement to the membrane potential closer to or farther away from this threshold potential, which is often around negative 50 millivolts. And we talked about how these graded potentials decay with both time and distance, so that as a depolarization from an excitatory input spreads along the membrane, the size of the graded potential gets smaller, and the same thing with a hyperpolarization caused by an inhibitory input. And we talked about how this decay with time and distance involves how much effect any of these graded potentials out here in the dendrites or the soma will have on the trigger zone at the initial segment of the axon. And that what's usually needed is multiple excitatory inputs causing depolarizations to have temporal and spatial summation, so that the size of these excitatory potentials can be large enough when they get to the trigger zone of the axon here to push the membrane of the trigger zone up over this threshold potential. And if summation of all the excitatory and inhibitory potentials at any moment in time brings the membrane potential of the trigger zone right here up over this threshold value, which is often around negative 50 millivolts, then usually an action potential will be started here at the trigger zone and conducted all the way down the axon. Action potentials being conducted down the axons of neurons are the way that neurons can transmit information over a wide range of distances, which may be 1 meter or more. Action potentials have some big differences from graded potentials in that they usually have the same size and duration for any particular neuron, and they are usually conducted the entire length of an axon basically unchanged regardless of the distance of that axon. The shape of an action potential is fairly characteristic, so it starts with summation of graded potentials getting it to the threshold value, but then instead of just decaying back down to the resting potential like graded potentials do, it has this huge rise to a very positive membrane potential, where it's become more positive inside the neuron membrane than outside, which is the reverse of normal, where normally it's more negative inside the membrane than outside. After this part, that's called the rising phase of the action potential, it has a short plateau, then it has a rapid falling phase back down to the resting potential. But it actually doesn't stop there. It keeps going more negative than the resting potential, then that plateaus, and then it has a bit of a slower kind of return to the resting potential from there. So the exact values may vary between neurons, but common numbers are that it might go from around negative 50, if that's the threshold potential for that neuron, all the way up to somewhere around positive 40 or so. Then it may come all the way down to around negative 70 or so before it's kind of more slowly settles back into a typical resting potential of around negative 60 or so. The total size of the action potential may vary between neurons, but for any particular neuron the size is usually the same, which is called the all or none property of an action potential. You either get an action potential or you don't get an action potential, as opposed to graded potentials where the size varies depending on the size of the input. So that if a depolarization leading to an action potential is just slightly over threshold like this, you'll get the same size action potential as a graded potential that's way over threshold. It doesn't make any difference how far over threshold you get. The size of the action potential will usually be the same. That's the all or none property of action potentials. The duration of an action potential is also usually consistent for any particular neuron. It's usually pretty quick, just a few milliseconds. Graded potentials can also be pretty fast. They can be a few milliseconds as well, but they can also be much, much longer than this. Graded potentials have a wide range of durations based on the duration of their inputs. Another big difference is that action potentials usually do not decay with distance like graded potentials do. Action potentials are usually conducted down an axon unchanged no matter how long the axon is. So that if we look right here at the trigger zone where the action potential starts, it'll have this kind of shape to its waveform. And then if we check maybe halfway down the axon, it'll have the exact same shape. And then if we check way down at the end of an axon, even if this is a meter or more, it'll have the exact same shape again. It doesn't decay with distance. The speed that action potentials are conducted down axons is often very fast. Can be anywhere from 1 meter per second up to 100 meters per second. A couple of things go along with faster conduction speeds for action potentials. Larger diameter axons conduct action potentials faster than smaller diameter axons. And myelinated axons, axons that have a myelin sheath, conduct action potentials faster than axons that don't have a myelin sheath. And that often goes hand in hand. We usually see myelin sheaths on larger diameter axons. With myelinated axons, the speed an action potential is conducted down the axon is not consistent. We actually see that the action potential is conducted faster through the myelinated segments than through the gaps between the myelinated segments called the nodes of Ranvier. So that if we look here at the trigger zone, the action potential travels a little slower through there, and then much more quickly through this myelinated segment. And then it travels a little more slowly through that node of Ranvier, then much faster through this next myelinated segment. This phenomenon is called saltatory conduction. Saltatory. And this word, saltatory, comes from a Latin word for jumping, because the action potential appears to jump from node to node instead of having a nice smooth conduction along the axon.